Welcome to the discussion. Today, we're diving into a research paper that tackles the complex world of online social media auditing. The paper proposes a mathematical framework to regulate the influence of algorithmic filtering on user beliefs and decision-making. Sounds intriguing, right? What's the core problem this paper addresses?
The core issue is the potential for harm caused by algorithmic filtering on social media platforms, SMPS. SMPS use app to curate user feeds, aiming to maximize engagement and revenue. However, this can lead to biased content, the spread of misinformation, and manipulation of public opinion, influencing everything from vaccine hesitancy to election outcomes. Current regulatory attempts often face significant hurdles.
So, how does this paper suggest we overcome these regulatory hurdles? Is it proposing new laws?
Not exactly. The paper focuses on creating a data-driven auditing procedure. Instead of relying on specific regulations, it proposes a system where an auditor, or even the SUMP itself, can monitor the impact of audits on user beliefs. This is done by comparing filtered feeds, what users actually see, to reference feeds, a hypothetical feed created without the platform's subjective biases.
That reference feed concept is interesting. How is that even defined? It seems like a very subjective thing.
That's a key point. The paper acknowledges the subjectivity. The reference feed isn't a single universally defined thing. It's a feed constructed based on a user's interests, without any manipulation to maximize the platform's rewards. The exact method for creating this reference feed is left flexible, allowing for different interpretations based on the specific context and agreement between the platform and users.
So the auditor compares the actual feed to this idealized, unbiased feed. How does that help determine if there's a problem?
The paper introduces a metric called belief variability. This measures the difference between the user's beliefs and actions under the filtered and reference feeds. The auditor then uses this metric in a sequential hypothesis test to determine if the platform's AF is causing an unacceptable level of influence.
A sequential hypothesis test. Can you explain that in simpler terms for our listeners?
Imagine it like this. The auditor continuously monitors the belief variability. If it stays below a certain threshold, everything's fine. But if it crosses that threshold, it signals a potential problem, indicating that the platform's algorithm is significantly influencing user beliefs and actions.
So it's a continuous monitoring system, not just a one-time check. What about the practical aspects? How much data would an auditor need to make these assessments reliably?
The paper provides sample complexity guarantees, essentially specifying the amount of data needed to make accurate assessments with a certain level of confidence. This depends on factors like the number of users, the complexity of the content, and the desired level of accuracy. The paper also addresses the computational complexity of the auditing procedure.
The paper mentions a worst-case approach versus an average approach. What's the difference?
The worst-case approach focuses on the user most susceptible to manipulation. If this user's feed is acceptable, then all others should be as well. The average approach, used in this paper, considers the average influence across all users. Each has pros and cons. The worst-case approach might be overly sensitive to outliers, while the average approach might miss subtle manipulations of a small group.
The paper also discusses counterfactual regulations. What are those?
Counterfactual regulations address scenarios like, should the platform show similar feeds to users who are identical except for, say, their political affiliation? The auditing procedure can be adapted to test these kinds of what-if scenarios.
This all sounds very mathematically complex. What are some of the key mathematical tools used in the paper?
The paper leverages concepts from distributional testing, specifically the tolerant closeness testing problem. It also deals with testing Markov chains, as the paper models the feed generation process as a Markov chain, reflecting the temporal dependencies in how feeds are created.
Markov chains? That's a pretty sophisticated model. Why use that?
Using a Markov chain allows the model to capture the temporal dependencies in how the platform generates feeds. The current feed isn't independent of past feeds. The algorithm learns and adapts over time. A Markov model captures this dynamic behavior.
So the paper provides a framework, an auditing procedure, and sample complexity guarantees. What are the limitations?
The paper focuses on a specific type of Markov model. Real-world platforms might exhibit more complex behavior. Also, the reference feed is a theoretical construct. Defining it in practice can be challenging. Finally, the computational complexity of the auditing procedure needs further investigation for very large platforms.
What are some of the next steps in this research?
The most important next step is real-world implementation and testing. The theoretical framework needs to be validated on actual social media data. Further research is also needed to explore more sophisticated models of user behavior and platform algorithms.
This has been a fascinating discussion on the challenges and potential solutions for auditing social media algorithms. Thank you for explaining this complex topic so clearly.